Hi, my name is Blake Teedy, and I attended the public lecture on this year's Nobel Prize in topological fields of matter and exotic states of matter. Now, it first was interesting to me when I learned that this is what this year's Nobel Prize went to, as beforehand I almost was assured that it would most likely go to the gravitational wave discovery. Mostly because we had so much exposure to that, because Georgia Tech researchers did play a significant part in that, and the fact that we finally covered a significant portion of Einstein's theory of relativity, and the fact that gravity does propagate in waves. I was maybe for certain that would be the subject, but originally when I saw that it was topological fields, first I had no idea what that was. I didn't know what topology was before I went to this lecture, and otherwise I didn't even know. I assumed it was a subject of physics that had to do with something so abstract that I would never understand it. However, going to this lecture really brought light to this topic to me, and made me appreciate the subject, and come to realize that the reason why that this subject won the Nobel Prize over gravitational waves is because it does have a much more real and impending use in everyday lives, and that's within quantum computing. So the study of topology is a mathematic concept. Essentially, it seems kind of hard to grasp, but topological figures are divided into different groups, essentially based on how many holes they have, such as 0 holes, 1 holes, or 2 holes. Looking online, I actually found a lot of information using Quanta Magazine and Wired and CNN sources like that, that essentially you can compare to different shapes topologically. For example, a picture frame, the outside, and a coffee mug both have, including the handle of the coffee mug, essentially both of them have one hole. The picture frame has the one hole on the inside, and the coffee mug, if you think, it has the main shape and the handle, which makes it one hole too. So topologically, both of those items would be grouped together in the one hole category. And in this physics Nobel Prize, we're talking about 0 holes, 1 holes, and 2 holes. Now, this may seem very familiar with other quanta ideas that you can't have a half a hole, you can't have 1.5 holes. Specifically, it is round numbers, and specifically in this area, we're talking about 0, 1, and 2. So, during the presentation, it was discussed how the winners of this year's Nobel Prize went about examining exotic states of matter. Now, exotic states are, they're not your basic solid, liquid, gas states. They mostly happen around very, very low temperatures, and they used to be thought that it actually can happen in 2 dimensionals, but as they found out, it can. So these exotic states were, since there's essentially, if you think about it, solid, liquid, and gas is a way that us as physical beings can describe and perceive different states of matter. Now, since we usually don't come about near 0 degree Kelvin things in our everyday lives, it's essentially kind of really hard as human beings to describe the different states of matter near 0 degrees Kelvin. However, these physicists connected these states of matter to the topological ideas of the hole, 0 hole, 1 holes, and 2 holes. So one thing that I didn't quite like about the presentation is he did a great job of explaining the concept, explaining how it connects to the quantum Hall effect, explaining how the scientists went about finding these different states and, opening up the whole world of exotic matter, which essentially, if we can summarize this year's Nobel Prize by one thing, it opens up more Nobel Prizes to exploring the different states of quantum matter. But he didn't quite explain, why we care about that, right? I mean, to me, missing this one puzzle piece, I still thought, why did they not give it to gravitational waves? Because I knew the importance of Einstein's theory of relativity. I knew that he could not prove directly that gravitational waves exist, even though it fit in the model. That by us proving it, it's just adding on puzzle pieces, such as 2013 when they gave the Nobel Prize to the discovery of the Higgs boson and the Higgs field. So that was a basic quantum particle that fulfilled theory of relativity, and missing the practical application of this year's, I didn't understand why they didn't give it to that. But really, to understand the practical application, you have to go into what is quantum computing, how does it work, and how does it benefit us. So essentially, in computing, you have two bits, two states. You have a 0 or a 1. We all know binary. Especially here at Georgia Tech, we like to play on, how smart the binary bridge and stuff like that. But essentially, computing is done using mathematical formulas, going down to those two simple bits. But in quantum computing, not only can you have the two bits 0 and 1, but you can also have a superposition of both 0 and 1. This greatly increases computing power if we can scale it up to anywhere near the size that we have normal computing. And learning about, how these different exotic states of matter work with different materials down to near 0 degree Kelvin. How that I learned while reading Quantum magazine that essentially you can't look at, essentially what this physics Nobel Prize was also about is they discovered that you can't look at the ebbs and flows of the electrons in different states of matter simply as each electron individually. You have to look at it as a group. And those groups correspond to the topological objects, topological shapes that they are assigned to these bits of electrons in these different exotic states of matter. Going back to the whole, the no-hole shape, the one-hole shape, and two-hole shape. I saw physicists explain it as a croissant, a donut, and a sweet roll, being 0, 1, and 2 holes, over at the Physics Nobel Prize. And essentially, those different states correspond how they could be used in quantum computing and stabilization in order to produce those computations using the three states, essentially, 0, 1, and the superposition that is used in quantum computing. And understanding those things are exactly what we need to learn about the materials in order to scale up quantum computing and make it a viable and not only very consumer option. So, in summary, essentially, I think the presenter did a wonderful job on explaining how this physics Nobel Prize went about. Seeing that looking at the audience personally when I was there, I could see that a lot of them were, the title of the lecture, exactly was geared towards physics-minded people. It was not for laymen. So in that respect, I think it did exactly what it was meant to do by explaining the Physics Nobel Prize to even other professors here at Georgia Tech. But for laymen, for people who are just getting into physics, who may not know the current news about quantum computing, and even get into much of low temperature physics, essentially. It didn't do so much a good job with that. I think he should have at least, gone into, seeing that we're all engineers here, gone into the actual practical applications of, this is how this would bring us this much closer to quantum computing. Towards the physics and mathematician, he did a great job, but towards the engineer, maybe not so well. But anyways, so again, my name is Blake Teedy, and thank you so much for watching this video.